Hmm. Okay, yeah, well, here we are. Um, yeah, okay, so let me try to get back. So last time we had some slight technical issues with Zoom, but so I should have like finished this part last time, but let me just get through where we were. So I was just discussing briefly this fact that one can incorporate some probability data on linguistic structures, in particular on parsing or on strings and on parsing, on parse trees. And so I was like just quickly going through what happens if you do some naive things like Bernoulli measures or Markov measures on strings of words. And the other get back to where I was. Yeah, right. And so I was discussing briefly entropies and measures of information for strings of text. And in particular, I went briefly through the n-gram models, Shannon n-gram constructions, where you just look at the strings of words and the probabilities of some piece of a word, next letter or next chunk of words, depending on how you parse things, how you subdivide some unit, depending on the previous one or the previous two, and how to combine these into hidden Markov models so that you kind of compensate for the fact that when you start to look at strings, you get some very low probabilities that certain exact strings of words would occur, but you can still get some combined probabilities where you consider the occurrences of single words, words given the previous one, given the previous two, or corresponding n-gram versions. And of course, these were introduced very early on. In Shannon that discussed this sort of funny examples where you can make randomly constructed things look more and more similar to actual language by changing the distributions. And in particular, so let's go to the last example that I was discussing last time. One of the things, however, is that just looking at strings of words, of course, as we already know, sort of loses a lot of the structure. And there's this famous example in English where you can have like the same lexical item repeated over and over, but you can parse it in different ways, in actual meaningful ways. And so the information content is, in this case, is entirely contained in the syntactic structure and not in the individual lexical items. And so this means that in some sense makes more sense to incorporate your probabilistic structure in the parse trees, or in the derivations that give you the sentence, so that you would actually be seeing the actual the structure rather than the string rather than just the string of words. And this would also the idea of introducing this kind of probabilities are also as a way to distinguish between different ambiguous kind of parsing that you can have, because you can have several ambiguous parsing, but given a certain context, some of them will be more likely than others, and will allow you to choose like a more likely interpretation than another one. So this a setting that can be made probabilistic in this way very easily is the case of context-free grammars, where you have this kind of production rules that assign to a non-terminal symbol a certain strings of non-terminal and terminal symbols. And one can assign probabilities to this derivation with the rule that you look at what are all the possible derivations that you have with a given non-terminal symbol that to begin with, and you assign the total sum of probabilities of those equal to 1. So it's a way of expand, you look at all the possible ways to expand the non-terminal in the derivations of the language, and you make that into a probability distribution. And so this, you can consider then the fact that, if I want the probability of a string in the language, I think of it as the sum of the probabilities of all the parse trees for that string. And so I can distinguish, like, well, some parse trees will have a lower probability and others will have higher probability, but this would correspond to count. So it's like a more structured way of assigning a probability to a string, which is not just this kind of like Bernoulli or Markov on successive letters, but it looks for all the possible generative structures for that string. And in general, one does this by certain kind of independent assumptions on subtrees in a parse tree. And basically, there are two independent assumptions that one makes. One is that the probability of a certain transition to a string of terminals or a string of leaves of your tree does not depend on anything. So if I have like a vertex that's labeled by a non-terminal, and I have all the leaves below that vertex, which is what you end up with in your derivation starting with that vertex, and you assume that the probability does not depend on anything else that's happening outside of that subtree. And the other thing is that you assume is that it's independent of everything that happened above that subtree. So you make this kind of independence assumptions on different parts of the tree. And if you do this, then you get what you expect, and that the probability that you assign to a whole parse tree is in fact the product of the individual production rules that end up building the tree. So, and each of them is independent of the other ones. So in this case, there's one production rule that replaces the non-terminal A with B and C, and there's two production rules, one that replaces B with a certain string of terminals, and one that replaces C with another string of terminals, and the probability of the entire tree factors out into the probability of these three derivation rules, the production rules in the context-free language. And in particular, there's for context-free grammars, one of the earlier results in the general theory of formal languages is that there's one can always put the production rules in a particular form. So in general, as I was saying before, you should really think of the production rules of a context-free grammar as being something like the presentation of a group. And so in general, of course, it's difficult to say when two presentations are equivalent or not. But here there's some situation in which you always have like a preferential form in which to put your presentation. And this is what is called this works for the context-free case, and it's called the Chomsky normal form. And it means that all the production rules are either replacing a single non-terminal with a terminal, or replacing a single non-terminal with a pair of non-terminals. This means that your trees are in general binary, because you're splitting a non-terminal vertex into two, so you can reduce your trees to be generally binary, except at the very last step where you have a single non-branching vertex that replaces one non-terminal by a terminal. So I don't think it's necessarily unique, but you can always put it in this form. If I remember correctly, is not necessarily unique. I'll have to double check whether that's not that. But the things so this means that once you have it in this form, if you want to assign probabilities, so you can look at a single non-terminal, a single internal vertex somewhere in the tree, and again, separate out the part that lies below that vertex with everything else outside. And you can look at two kinds of probabilities: the one that takes care of the interior part below that vertex, and one that takes care of everything else that happens outside of that piece. So you can have inside probabilities that look at the string that you get at the leaves of that subtree relative to what non-terminal you have at the root of that subtree. And then everything else that depends on what happens outside of that subtree. So the other leaves and out and the left that's saying where you are in the tree, right? Which part you're cutting off. And so this particular Chomsky normal form for the presentations of the grammar allows you to get a recursive way of computing these probabilities. So essentially, because you know that at each step you have a splitting like this, which is this binary piece, and then these other subtrees. And so if you wanna like the interior probabilities for these all three, it reduces to two pieces separately for the corresponding splitting. And so this in particular gives you a recursive formula for these probabilities of what happened inside the subtrees in terms of all the possible binary production rules with non-terminals and the corresponding probabilities associated to these smaller blocks, which are a smaller size. So it is a recursive construction for these probabilities. So in general, where one gets these probabilities is from some kind of training data, some kind of training corpus. And in this case, of course, since you want to assign probabilities to the actual parsing structures, not just to the texts, then you need some kind of corpus that incorporate different possible parsings, and and you want to assign probabilities to those parsings. And so this can you can consider it in terms of, again, kind of hidden models with hidden nodes that correspond to these transitions that are just among non-terminals and the corresponding probabilities that involve the leaves. So I'm just going to go quickly over this because, as I said, I will come back at some point later on to discuss the use of probabilities. And this is kind of a version that's based on parsing by context-free grammars, which is not necessarily the ideal way. But I mean, one can see that, for example, this kind of assignment of probabilities allow you to distinguish between certain possible ambiguous parsing on the way of using information from context in the given corpus in which you are coming across one or another of these versions. Of course, the thing one can ask is what about like going beyond this context-free case? To what extent this way of assigning probability to parsings can be extended. So over time, as I said, there were various classes of mildly context-sensitive grammars that are being considered. And one of them is these three adjoining grammars that I described briefly in a previous lecture, where you have these two types of operations on trees. One is the kind of operand composition that glues together one of the leaves with the root of another tree. And another one is this insertion at an internal vertex of the tree where you plug in, you kind of split it up and plug in another tree with the roots attached to the top part and one of the leaves attached at the bottom part. And so you have these two types of operations that you can do, and you have all possible ways in which you can perform one of these operations, substituting a certain tree, attaching it the first one is like this operand composition, and then an adjunction of another tree, which is this vertex insertion. So you have a certain set of all these possible operations that you can perform on a given collection of trees. And you can assign probabilities by assigning probabilities to these various operations in a way, again, that starting with a certain tree, the sum of all the possible probabilities is equal to 1. And this is so the way that this gives you, again, a kind of probabilities associated to the entire parse structure, entire derivation in a three adjoining grammar. And so if you have like a chain of derivations in your tree adjoining grammar where you perform a sequence of these operations on trees, you assume each of these to be independent and assign probabilities accordingly. And there are some other cases in which, beyond the context-free case, where a similar approach to assigning probabilities to some extent works. The multiple context-free grammar, there's some things that have been discussed there. And for these merged grammars that I was mentioning, it's more difficult, but I'll come back to discuss more in detail these things later. But I just wanted to give like a very quick overview of some of these ways that across this kind of historical development of various stages of generative grammars, probabilities have been incorporated in this. Of course, there's some question overall about what is the role of probabilities in this analysis of how the generative process of language works. So, in the calculation of syntax is a completely deterministic process. I mean, it has its own rules and it functions. There's nothing which is probabilistic a priori, with this process. And of course, this is like all the objections that the notion of a probability of a sentence doesn't quite make sense if you take it at face value, which is true if you're trying to assign probabilities to sentences in a large corpus. These probabilities are going to be astronomically small. They don't really make sense. In fact, this is not what for example, now the large language models, of course, they are probabilistically, but they are probably functioning in an intrinsically probabilistic way. But that's not what they're doing. They're not assigning probabilities to sentences in a corpus. They are computing probabilities to the generation of sentences by extending text, but they're not they're not really attempting to extract probabilities of sentences to corpora. So in this sense, it's true. I mean, it's not, there's no, when one talks about these probabilities of parse trees and so on, it has to take that with a grain of salt of what it actually means. On the other hand, there's a kind of lesson to keep in mind, that the fact that a process is deterministic doesn't mean that probabilistic methods are not useful. So, for example, let's just take an example from mathematics that's completely different. Now, let's think about prime numbers, right? So prime numbers are also kind of generative process. They are the generators of the integers in the multiplicative sense. And they're a completely deterministic system. There's nothing probabilistic about one number dividing another. Either it does or it doesn't. It's not like it does it 30% of the time. So of course, that's on the other hand, there are many ways in which it makes sense to consider primes as being like independent random variables. And there's a lot of arguments about properties of prime numbers that can be proved using probabilistic method. There's a whole field of number theory that is called probabilistic number theory, and it actually does prove completely deterministic results about completely deterministic objects using probabilistic methods. So in what I want to say as the punchline of this discussion is that in linguistics, one should take a similar point of view, that the actual things that one is trying to describe are deterministic computational processes. But one can keep in mind the fact that the use of probabilistic method can be helpful in proving things about deterministic computational systems. So that's so so this is just very quick view of the, let me change to another set of All right, so here we're kind of at the last step of this kind of historical overview of the development over several decades of generative linguistics. And so this is actually what happened now very recently with respect to this whole story. So this is, I'm going to give a very quick summary, because then I will actually be talking about this for the rest of the class. So I'll go into the specific definitions and details in a moment. But I first want to give like a very quick bird eye view about what this is about. So this is essentially what happened during the last 10 years. And it's part of this idea of a minimalist model based on this operation that were originally described as merge and move that I talked briefly about before. But it's sort of redesigned to try to, in a sense, capture more closely the basic fundamental computational structure underlying the differentiation between different languages. And so there's a bunch of other references. I just put down some of them here. They are also on the webpage. The last one is this short book that actually came out last December. So it's we are getting as close as as present day as possible. You can also download this one from the webpage of the class. And so what I'm going to do very briefly is kind of glance through what is in this book here, and then I'll start reworking through that with the mathematical formulation, which is the same thing, but said in a way that is more familiar to mathematicians. So this is the book that I'm talking about, and so what goes under the name of Strong Minimalist Thesis is essentially two hypotheses. And one of them is that all the structures that pertain to I language, by I language means that this kind of internal calculator of language, which is prior to differentiation into specific languages with specific different rules. So all of the structures of I language are generated by a single operation, which just goes under the name of merge. And the second assumption is that of this thesis is that this arises as a kind of optimal solution to a set of constraints. So this second assumption has two forms. If you look in this literature of the last few years, let's say a much stronger form and a somewhat weaker form. The somewhat weaker form is the one that I stated here, namely that this model of the I language as generated by this single merge operation is itself an optimal solution to constraints. The kind of stronger form is that everything that actually pertains to the faculty of language as a whole is an optimal solution to constraints. This, of course, second version is much harder to prove than the first version. So I stick to the weaker form of the statement, which I think is something that can actually, to some extent, be proved in a rigorous way.
What constraints that is language specific, or?
So that will, yeah. So there will be constraints that has to have to do with the differentiation into different languages, and constraints that are intrinsic to the old thing. So in a sense, there are one thing that is that there are essentially the kinds of constraints. One is like our own biology, right? For example, partly how our brain works, which in large part we don't know, but partly is how our vocal system and so on function in the way that we have to use language with when our expression of language passes through the way that our body is built. So that puts some constraints. For example, the fact that language is externalized as a time ordered sequence of sounds has to do with the way that our body is built. It's our biology. There's nothing, that puts some constraints, right? And the other constraints are things that are learned. The differentiation between languages is partly acquired because we learn to speak one language rather than another. So there's some process that but sometimes linguists refer to it as parameter setting that, makes us learn one language, learn the rules of one language. So makes us specialize our, language calculator in one way rather than another. And then there are like laws of physics. So in that sense, there's part of these optimization constraints. You want to think of them as being something that maybe optimize like the whatever cost in whatever sense, energy, information, complexity, something of the calculations that are involved. So these are, in a sense, the kind of constraints that one can expect will have to be described and accounted for in some way in the model. So in a sense, one of the main points of this change of perspective in this last model is that in pretty much everything that I talked about so far, whenever we were discussing parse trees, the trees were always planarly embedded, and the leaves are all, as a consequence, were always ordered in a specific ordering. And one of the steps is to say that, okay, this ordering is actually, in a sense, not part of the key structure, is something that is forced by the fact that as we speak we actually have to use time order sequences of words, and so we have to have that type of planar embedding of parse trees. But the actual structures that our calculator deals with are abstract trees, or if you want, non-planar in the sense of not embedded in the plane trees. So in a sense, like rather than sequences of code of digits or letters or words, language, you should think of it as something like these Calder mobiles that are like freely floating, and not where the leaves have no fixed predetermined order.
These two are supposed to be equivalent, or one is more informative than the other?
Yeah, so the idea is that these structures that are non-planar are like the fundamental ones. And then, so they are the ones that get computed in one way. And then, depending on how your sort of process of language learning that happened, they will get, they will acquire planar embedding that is consistent with the word order properties of one language rather than another one. But they're sort of a priori computed just as these abstract structures.
So in a sense, they have more information, right, in the planar case, because you could write it in a way that represents the actual structure with parentheses or whatever, but then it's also adhering to the word structure of one specific language.
Right. So yeah, I mean, it's just the ones the planar will necessarily depend on one particular language, whereas these underlying structures, they don't they can't just be universally built regardless of which particular language. And of course, some of them will be consistent with the syntactic rules of one particular language, and others will not. So there will be like some filtering. So the idea is like in this model you kind of separate out two different. So instead of trying to build a structure while at the same time keeping into account the rules of one particular language, you kind of separate the two processes. You have a freely building mechanism, a freely built structure, and then a kind of a filter that is language dependent, for which certain structures will survive and certain will not, depending on which language you have acquired.
But can you apply that kind of filter and represent it graphically, or that's not?
Yeah, so you can. Yeah, I'm gonna. Yeah. Yes, I'm gonna say more about it. Yeah. So there are various things that happen that take various ingredients that go into building this model of this basic syntax universal syntax calculator. And So I will just quickly give as I said, a kind of preliminary view on these things, and then I will give specific definitions for all of them. So the basic beginning level is that your fundamental building blocks are lexical items with certain syntactic features that tell you what role these lexical items will be playing in a sentence. So you can have things marked as being verbs, marked as being nouns, and so on. All languages have a notion of what a verb is, or what a noun is. So you have this kind of classes of possible features in the syntactic sense that makes sense for an arbitrary language. And the lexical items, of course, specifically, they will be embodied in specific lexicon of one language rather than another. But a priori, you can think that there is like some kind of conceptual space where you associate words to concepts, and you can think of lexical items as living there, and then being attached to a specific dictionary of a specific language. Right. And syntactic objects are the basic structures that are built out of lexical items. So when you try to start to combine them into structures. And workspaces are a kind of a scratch pad where different steps of calculations can happen at the same time. It's like what you upgrade every time you make a step of your derivation, and where you draw on additional computational material that you have not used in the previous steps, and that's still available for calculation at the next step. And there's a further notion that's actually useful in the sense that, as I was discussing already a few times, when you don't just build structures in a language, but you also modify structures that are already built. You can manipulate sentences that are already formed. And usually to do that, you have to access substructures into a sentence that's already formed and extract them and recombine them. And so accessible terms are the substructures of a structure that's already formed that are accessible for further calculation if you are modifying a structure that's already existing. And so this operation of merge, one can think of it as a kind of a dynamical system on this set of workspaces that keeps updating workspaces and transforming and building structures. So this is like this basic structure building operation. On top of that, there's additional linguistic data that are these things that I'll talk about more later. They're called phases, labeling, and theta theory. So phases are the fact that you build substructures, and certain substructures are kind of complete in themselves. Complete in the sense that they are already parsable for meaning, for example. So there's substructures that stand on their own, and there are substructures that don't stand on their own. So phases are like complete substructures that already stand on their own, and they can be part of larger sentences, but they can also already be parsed as independent substructures. And this, in some sense, I'll say that more precisely later, has a bit of a similar feel as, if you're familiar with models of physics where, one does this kind of like, for example, if you have spin systems, like in physics, you can combine together certain blocks, spins, and freezing them as a single entity. That you no longer look at the fine structure inside those once they are blocked. And so these phases are a bit something like that. So once they're built, you can think of them as structures where you no longer take access substructures anymore. And then that has, in a sense, the same effect as you have in physics, that, it allows you to remove a lot of degrees of freedom and reduce the explosion of the number of degrees of freedom. So here, it will be a way to kind of curb the combinatorial explosion of certain calculations. Yes.
Yeah, I just, when you're saying phases, it's not like in the sense of different phases of matter. It's more like blockchain.
That's right. They're called phases because you kind of build them one after the other. So you say you are in a higher phase or a lower phase.
Okay.
But it's like
it's not like liquid phase or solid.
No, they're really like phases of your construction, right?
Yeah.
But it's really like blocks. It's really like block spin, because you say once you close up one of these blocks, you think of that as frozen, and you no longer pick finer structure inside that. I'll say it more precisely later, but I just want to give a sense of what these things are. And labeling is a way to kind of go into the tree and kind of keep the old examples that I was making, the things like that if something is a noun and you combine it with an adjective, you get something which is a noun phrase, and so you label the vertex above as noun phrase or something. So you try to build an algorithm that kind of labels the internal vertices of a tree so that you know what role the entire structure has. And there are rules of when you can do such labelings or not. And theta theory has something to do with roles that mandatory roles that certain syntactic relations have. Like, for example, if I take a case where I give something to someone, right? So this give is a verb, but it calls for two things. It wants a direct object, and it has like a dative type relation to, there's something that you give and there's something that you give to someone, and there's a subject that is the giver. Right? So these are like they're called thematic relations, and this is the reason why it's called theta theory. Theta is for thematic. And so certain things mandatorily have to combine with other kind of elements. So something gives a theta role and something takes a theta role, and these things have to match. And
so data reduction is one specific example.
Yeah, so in this case, like you give something to someone. So that's a different kind of thematic relation than giving something or that someone giving. So there are these different kinds of roles that you have to say that they have to match. If something is combined in a certain way and it's a giver of a certain kind of theta role, what it combines with has to be a taker of that same kind of theta role. Okay. Yes.
Is there a type theory for these things? So certain things have to have a certain type when you combine these phases?
Yeah. So no, I will describe how this works much more in detail later. I just want to give a sense of what these things are, but very end waving for the moment, right? And then there's like two channels, right? So this is this computing structure building operation of syntax, and then the products of this go to two interfaces. One is called externalization, and it's the interface with our sensory motor system that makes the language external, either whatever way, either by speech or by writing or by sign languages. But it's there is the part where this externalization is now language dependent. Is no longer something that's universally functioning for all languages in the same way. That is where the way that it gets externalized becomes dependent on specific acquired, learned rules of specific languages. And the other interface is what they call the interface with the conceptual intentional system, which is also called the syntax semantics interface, which is the fact that these syntactic structures have to be parsable for meaning. So the substructures have to come together in a consistent way so that they can be parsed for meaning. And of course, some of these previous parts of the picture, like phases, labeling, and theta theory, are designed to make help the parsability of the resulting structure in terms of assigning semantic values to them.
But they are helping only with the syntax, right? Not the semantics.
Yeah, so here, that's right. So this is kind of part of how you build the syntactic structures, but somehow some aspects of it are already designed so that it will make the interface with semantics more somehow more functioning, right? Because you have some hints, it already carries some information about how things should be parsed.
So we're starting with lexical items and then you're also going all the way to semantic. So it's like
that's right. So that's right. So the part of this that actually are already in some way interfacing with semantics are, well, the lexical items themselves to begin with, and also the syntactic features, because they're already, knowing that certain things play certain kind of roles. So the concept of what a verb is, of course, is part of syntax, but is also part of semantics in a way. And of course, the lexical items are associated when we learn words, we learn them associating them to some semantic content. And these other parts are also somehow designed to make the interface with semantics possible. Okay, so these are like the main ingredients of this model that I'll have to go through and discuss more in detail. Right. So the way this is illustrated, you have a kind of lexicon available, a set of lexical items and syntactic features. A bunch of them are what you start your derivation from. So you are building a sentence. So you start with a certain set of or multi-set of lexical items and syntactic features. And then your workspace get updated every time you perform an operation with merge, and so it will contain partly built structures and other of these basic building blocks floating around that you keep assembling together. So the way this is described as a simple description is that this merge operation looks inside your workspace and targets certain particular material that you want to use for the next operation, builds a new structure using that material, and adds this new structure to what remains of the workspace and updates the workspace in that way, so that you can then continue with another operation. And like this is kind of an example. You have a bunch of lexical items. Of course, the examples you build them using a specific language, because necessarily you have to do that. But you should think of these are like the corresponding lexical, semantic lexical, and you kind of start combining them together until you form a unique structure that is a sentence. Again, these kind of three like structures you are not, write them down as a planar tree, because the example they're just taking it from some actual language, but they're just the structural relation between the words. Yeah.
Can I see the workspace as like an algebra over
something? I'll come to I'll come to some of these things. So some of these things in a moment. Yes, that's. And so then, okay, you have this building operation, and then it goes through these two different externalization and syntax semantic interface. And of course, these two in turn some way interact, because you're not just a producer of language, but you're also a receiver of language and a parser of the language that you receive. And so you receive something that has already been externalized, and you have to kind of undo this map, and then and at the same time parse semantically. So these two channels are, of course, interacting with each other in the parsing phase. And so what about this idea that this kind of operation should satisfy certain forms of optimality? And so, well, so for example, a priori, you can assemble together any number of things in a single structure. So your merging could be like some n-ary operation of arbitrary arity. And so one first optimality constraint is that the binary one should be preferable in terms of some optimization over the operations with higher arity. And I'll explain what that optimization is. It is indeed the case. And another kind of optimality constraint, and this is, I will explain more in detail later. A priori, you have different possible kind of forms of this merge action that can occur. And the one constraint is that among these, the optimal ones should be the external merge, which is just the one that combines two sections into a single one, and something like internal merge, which is the one that's responsible for movement, so extracting a substructure and doing it somewhere else. And this is the example that, for example, in English is evident when you make a passive form or something like this. And so I'm not saying anything yet about what this optimality constraint is, and I will explain it more in detail after I give the precise definitions of everything. But there is there are two kinds of optimality constraints that have to do with these two particular forms of merge. One is called minimal search, and another is called like a minimal yield or resource restriction. And I'll define more precisely what they are. And another kind of constraint that is assumed for this model is that this operation, this structure building operation of merge, is Markovian in the sense that it doesn't have, it has only memory of the workspace that you have available at a given time and not of the previous ones. And or if you want that, it defines indeed a Markov process on your set of workspaces. And again, this will have like a precise statement of well, in what sense it is indeed the case. And yes, yeah.
I know you'll talk about the optimization constraints, but if you think about it a bit more philosophically, choosing to have only a binary operation on any, the operation that's encoding structure in your workspace, isn't that like saying you're only considering nearest neighbor, like you're not considering pairs of 3 grams or 4 grams or something like that?
Yeah, in a sense, it's yeah, that's right. In a sense, it's like that. And you're saying that if you have an n-ary operation, it really is a composition of binary operations rather than having an actual n-ary operation. So in a sense, yeah, you can say that that's your maybe leading order term as opposed to the other possibilities. I'll say a little bit about that at some point later. Not yet. But so yeah, there's another so there's a few other properties that are discussed in the form of this model, and that I will describe more in detail. So one of them is this fact that when you perform this kind of movement that I showed in this kind of examples where you extract the subparts and you move it somewhere else, what happens is that you kind of forget about the place where you actually have taken this substructure, but you don't forget that completely in the sense that when you parse the sentence, after this movement, you sort of know that the piece that occurs somewhere else for reasons of syntax actually corresponds to something that was originally in a certain place. Your interpretation of the sentence knows that that piece belonged originally in a certain place. So there is this cancellation of the deeper copy of the part that you have extracted, that however keeps something that in linguists call the trace of where it was and what role it had in the position from which you move it. And yes, so then of course there are the other aspects of the model are the specific language dependent assigning of linear orderings and depending on syntactic parameters of various languages, and these other things that I talked about, this phases, labeling, and theory, and the interface with semantics. And in particular, in the relation to semantics, these external and internal merge play slightly different roles that I'll talk about later. So these are all things that I kind of described in these papers and this book from last year that worked on in the last 10 years. And so this is like a very quick bird's view on what are the ingredients of the linguistic model. And so the goal for the next bunch of lectures, the thing will be to try to turn this idea of the strong minimalist thesis into a natural theorem, where everything is sort of more mathematically describable. Okay, so before I move on to do it, let me just try to justify my existence into this into this story. So why do you want to do that, right? I mean, so when I give this talk to a linguist, I always say, no, I know the objection was going to come, and I said, okay, you have this book that I just talked about that published last year, that is like less than 100 pages, written for linguists, very, very nicely written, and so on. So why do you want to turn it into 400 pages of mathematics? Why do you want to do this? So it's it's a legitimate question, I have to say. And so the answer is that, for example, what that does for you is that a lot of these properties that are described as assumptions that are reasonable to make about the model and that have an empirical ground for why they make sense to be that way, a lot of them just fall into place as something that you can prove from a given basic formalism that accounts for the correct definitions of things. And so, in a sense, you can say, okay, here's now a model that proves all these properties, and you have the empirical grounds that confirm that these properties are what you expect them to be. And in a sense, that's the same way that you can think about when you do physical models of physical phenomena, where you have, of course, you have empirical reasons for why you think of modeling something in a certain way. But most of the time, what is really successful, historically have been extremely successful in theoretical physics, is that you let the mathematics do the heavy work for you. You kind of have a machine that makes a lot of things in the model determined by the algebraic structure, the mathematical structure. And then, okay, you can check whether the things that are determined match what the empirical reasons and the empirical data are like. So this is, in a sense, the idea of trying to treat the questions about language in the same way as you would treat questions about physical systems. Yeah, so that's I would justify my interest in this. Okay, so let me just get down to the next. Okay, so let's start again from the beginning of this story, and let's try to see what is happening here. Okay, so this is actually everything that happened during this last year, and so there's some papers there from last year, and they're actually now combined with a lot more additional details into a book that's going to appear. And you can download it also from the webpage of the class. It's kind of hopefully, well, it's not copy edited yet. So there's still a bunch of stuff that will be corrected, but yeah, so basically, there's these two books are sort of written in a way that can be, at least, the first chapter of our book follows pretty closely the way things are presented in the other book, except one of them is sort of written for linguists and the other for more mathematically oriented, either linguists or mathematicians. And the key point is to actually try to show that whatever is happening, that it has some kind of structural necessity to it. So this is the way where we are. So let's start to go through some of this list of ingredients that I quickly discussed before. And we'll try to get the corresponding more precise mathematical formulation and the corresponding properties. So there is this at the very basic heart of this core computational process of structure formation, there is this building of hierarchical structures as non-planar binary rooted trees. And so you have non-planar binary rooted trees that are decorated at the leaves by your set of lexical items and syntactic features, and then they sort of hierarchically combine into higher structures. So I will come a little bit later in so I'll start describing not immediately, but I'll start describing some ways in which the algebraic properties that I'm going to describe of this model resemble pretty closely other similar algebraic structures that occur in physics, and that have to do with Feynman diagrams in quantum field theory and the problem of, so I mean, in a sense, with the parallel, just to throw it on the table to begin with, although I'll come back to talk about it a little later. But the idea is that in physics, when you deal with structures, combinatorial structures in quantum field theory, you're expanding out some kind of symptotic expansion into perturbative expansion into Feynman diagrams in field theory, and you want to assign to each of these objects a corresponding meaningful physical value. And of course, usually you have a problem, because usually you don't have a nice, meaningful physical value. You have a lot of divergences that you have to get rid of. And the key point about how you do that is that it has to be done consistently over all substructures. And this is the problem of renormalization in quantum field theory, is exactly the fact that this extraction of meaningful values has to be consistent over substructures. And of course, in a sense, here the analogy, which ends up being more than an analogy because it will build on the same mathematical model, is that extracting meaningful values consistently over substructures, as you do in physics, is very similar to assigning semantic parsing consistently over substructures in the case of parse trees, in the syntactic parse trees in linguistics. And in fact, it turns out that the algebraic formalism that does these two things is the same one that does it in the same way. Okay. So let's come to the first thing, which are syntactic objects. So these are described. So one of the earlier papers on this version of the model as this merging of lexical items together to form unordered sets, and further enlarging them by continuing to repeat this binary set formation type of operation. And this, of course, mathematically speaking, is a well-known kind of structure. You start with a set, which is it's a finite set. It's possibly very large, but final, which is the lexical item and syntactic features. And you form the free magma on that set with the binary operation. And so what that means is that you have so in this case, it's the free non-associative commutative magma. And so you have a binary operation that is commutative but non-associative. And what you do is a sort of you start with the elements of your set, of your generating set, and then you already define new elements, which are the result of applying this binary operation. You keep iterating that. So, and the resulting magma has a binary operation acting on it.
Question. So it's commutative solely based on the fact that you're not caring about ordering planar.
Yeah, exactly. The commutative is saying that you're not caring about this linear ordering of your lexical items.
Okay. And this magma is built not just over lexical items, but also syntactic features, you said.
That's right. Yeah. So yeah, exactly. So in the sense that, for example, like when you do this parse piece for the buffalo sentences, you remember that some of these are going to play the role of. So the lexical item is the same, but the syntactic features vary because some of them are going to play the role of a verb, because some of them will play the role of a noun, and so on. So you have syntactic role of that kind that you can keep track of.
So it will just be a set of lexical items, but you're saying that the syntactic features in the magma are somehow built in together with the lexical items?
That's right. So you consider that as a set that combines lexical items and syntactic features as a single set. So this is going to be the point is just that this is a finite set. It's your lex in a language. Of course, you can have an enormously large lexicon, but it's still going to be finite. Unlike the set of possible sentences or in the set of possible structures here would be the elements of the magma, and that is of course infinite. But the generating set of the magma is possibly large, but still finite. Yeah.
Just to make sure, so the alpha is both the lexical item and its possible grammatical.
Yeah, that's right. So I'll show in a moment when I discuss this cancellation of the copies why you want to keep track of the possibility that you just want to remember a syntactic feature. Yes. Rather than a lexical item made together with a syntactic feature, or you might want to just have a lexical item. So but yeah, that will still be a finite set. No.
Yeah. Yes.
So why free? One more question.
Yes.
If you're talking about constraints and so on, and then you're letting it just be a free magma, then it's just like saying it can be anything, right? It doesn't matter how you combine the lexical items and syntactic features and so on.
You mean if you also allow n-ary operations or?
And I mean to say you've chosen this subcategory of magma. It's free, non-associative, commutative.
Yeah.
So non-associative is obvious because it's a tree. Commutative is because you're not choosing.
Because it's non-planar, right?
What about free? Can you say a bit more about?
No, I mean free. It really just means that the only relation, right, that you have in the magma is the commutativity relation. There's no other relations.
Yes, but I'm saying, why are you not hard coding more relations in when you're also talking about things like constraints of that it must adhere to as an algebraic description? Or do you just not care about it at that fundamental level?
You mean if you want to impose relations on the magma?
If you want relations, that's what
if you want relations on the magma. So yeah, I will come back to this. I mean, because for example, you could say, what about if I want to specialize to a particular language and I want to impose some relation on the magma that correspond to rules that I have in one particular language? So I'll come to discuss why I don't want to do that. But so for now, I don't want to impose. So this is this idea that there is this freely forming operation that freely forms structures, and so which corresponds to this being a free magma. Where the only relation is this fact that tells you that you're not imposing a linear order, and so your trees are non-planar. So the commutativity relation is the only one that you impose. And other than that, you just allow a like free generation of all possible structures that are built this way. And as I said, at some point, you will want to introduce some kind of filter that will tell you that some of these freely formed structures are not viable according to the constraints of one particular language. But the point is that if you want, I don't necessarily want to impose that once these structures are formed, that those filters would have to be morphismal magmas. They might not be. They might just be like portions of, say, vector spaces or something. You're requiring a lot if you impose that they are morphismal magmas, which is unnecessarily strong as a requirement. That's the reason why I want to impose it at this level.
Yeah. Oh, well, that answers my question. I was just wondering that. So, for instance, like ungrammatical constructions that would eventually be filtered out.
Yeah, exactly. So this will contain a lot of structures that are not going to be grammatical in some specific language later on, or they might not be parsable at all because they might not admit like a head function or label not be labelable as structures. So this just freely forms everything that can be. So it's like you have, so the idea in this model is like you have this calculator that freely forms arbitrary structures, and then the learn part is what builds some kind of filter that kills off a lot of this stuff.
So the structure that's there in the I language is supposed to be just the structure. Like that's what
right. So the idea here is that like the core mechanism for the I language is something that's as simple as it could be, because somehow that's you in a sense it's again this idea that you want to be able to like justify the fact that it's something that on the evolutionary scale came up in a really quick amount of time, and so for all the other things it has to kind of rely on things that were in a sense already existing, and you want to introduce the minimal amount of additional structure that would make it work.
So there are a lot of empirical evidence that suggests that, internal language should be like this, where you don't care about grammar, you just care about these. The only things you care about are the things that are encoded in some kind of binary structure.
That's right. So, I mean, I think that there's quite a bit of when people study the way that children learn to form sentences, and the very first thing that they learn are this sort of structural relation between different elements of the sentence. So this kind of the first thing that go into place are like the certain elements are related to other elements, not necessarily by proximity, but by like structural relations, and then that gets refined into the. So there's some kind of empirical evidence that the key very basic thing that starts to go into action is this basic structure building operation, and then on top of that everything else grows, so to speak. So that's just...
But you believe that it's at the fundamental level as simple as that, or do you think there is some missing ingredients that you also want to add?
No, of course there are lots of ingredients that have to go into this, but in some sense, if you want to say like what is the basic computational mechanism, that I mean, of course I'll come to. This is not the whole thing. This is like what are the basic structures that
I'm asking about the basic structure. Do you think that this basic computational mechanism, just this binary operation, is enough for a language?
It's enough for building structures in language. That I think there is enough empirical evidence that structures in language are tree-like, so that we don't need like the aliens of arrival that speak with graph that are not trees. I mean, but I think human languages, the structure building operations seem to be well accountable for by this kind of tree structures. Right? Okay, so of course this is another fact that's well known, that the free commutative non-associative magma on a set is canonically isomorphic to the set of abstract binary rooted trees with leaves decorated by that set. So syntactic objects are the same thing as binary non-planar, I mean, abstract non-planar binary rooted trees where the leaves are decorated by this set as associated. And okay.
Internal nodes are not labeled.
Internal nodes are not labeled. There's no labeling of the internal nodes. I will come later to this issue about labeling algorithms, which is part of this detecting which structures are not filtered out, which ones are filtered out. But at this structure building process level, there's no labeling to the internal vertices of the tree. So if you look in the linguistic literature, you find a lot of discussions around using the tree notation as opposed to using this kind of set notation for these syntactic objects. And there's various ways where various places and say, oh, this tree notation is confusing, and it should be preferably it's better to use this kind of set notation. And of course, there are the main reasons for that is that, of course, if you literally write a tree, you necessarily are writing it in the plane, right? Because you're writing it on the page. So it's easy to get confused about whether you're actually meaning a planar tree or a non-planar tree. Whereas with this notation, one usually puts like round brackets if you mean it an oriented, an ordered string, and curly, bracket if you mean it an unordered string. So it's completely clear if you're talking about an abstract rather than a planar tree. Okay, I mean, and the other thing that mentions a possible source of confusion with using the tree notation is exactly this thing of the labeling of internal vertices, because in earlier versions, like with context-free grammars, and one usually had, carries on labeling of the internal vertices by these non-terminal symbols and so on, whereas here you don't. And so, they're keeping the same notation. So obviously people are used to one interpretation of the tree structure, can be confusing. So if you go to the linguistic literature there, so I mean, I think we don't really have to worry about it, because, as mathematicians, we're completely used to, we're thinking of, if we just say, okay, the tree is not planar, fine, it's not planar. So not to worry too much about it. So I will ignore all the notational discussions that the linguists often have. So, coming down to what is the very basic thing, right? If you want the key fundamental, computational operation is this formation of binary rooted trees. And you can also temporarily forget about the labeling of the leaves, and you just have a single for structure formation operation like this. And so you can think of this generative process as encoded in a recursive structure. And so, well, let me just say right away, because I'm going to use it everywhere in a moment, that of course, if you have a set, you can always form the vector space spanned by that set. And of course, it doesn't matter really over what, or you could just think of it as a Z module rather than a vector space, but it's just convenient to form formal linear combinations of objects. And so in particular, if you do it on a magma, this vector space will have the structure of a commutative and non-associative algebra coming from the commutative and non-associative magma, which is not so important, because I will talk about a different kind of algebra structure in a moment. But this vector space in particular is also graded, because you can grade it. These are binary binary trees. They are full, not necessarily complete, but they're full. So you can grade it either by number of leaves, or by number of vertices, or by number of internal edges. They're all equivalent.
So this is just like a version of fine summation.
Yeah, right. And so if you want to encode this entire generative process of this magma, you can do it by a single fixed point equation, where you formally write a variable that is an infinite sum of variables in each degree in this space. So this is exists, if you want, in a formal completion of this vector space, and then you write this fixed point equation. Okay. Of course, this is completely equivalent to describing the generative process of this magma, because you can solve this equation inductively by degrees. And
sorry, you did something on the last slide, which I think was because before this you were talking about the graphs as just being composed, generated by left and so on. But here now you're saying it is a Z module, and it can be a little bit of this plus a little bit of this and a little bit of that. So now your magma is taking in as an input something that is a bit more diffuse.
Yeah, right. So well, so far I've done this just in order to be able to formally write this equation. Yeah? And so I formally write it so that I have a variable in each degree, and then I just write this fixed point equation. And so I'm just encoding in this equation this process here. The reason why I'm saying that I'm doing this is because if I want to solve this equation for these variables, of course I see that this is is going to be recursively defined in terms of lower degree terms. And so I basically have exactly all the terms of my magma will occur. And of course, several of them will be the same because it's of the commutativity relation. And in fact, I'm going to count some multiplicities that you tell me what would be the number of different planar structures that I can impose on each of these. But they are so the actual solutions in this could correspond to like an enumeration of all the elements in the magma and this operation is the one that composes the next ones from the previous one.
So degree is determined not just by depth, but by a number of, I mean, X4 has the second term is.
That's right. X4 just means that, right, I'm applying, at this point are all the structures that I obtained by applying, three times my M operations.
So what about the second?
So there are trees that are so now my leaves are not labeled. They're all just pending. I have the same letter everywhere, so I can plug in other items if I want. But so this is just telling me that I'm getting the different tree, the different non-planar trees on 4 leaves.
So it's just any tree that's formed by 3 operations.
Yeah, exactly. Of course, they are with the corresponding multiplicity. Okay, so I mean this process here, it's a recursive solution that describes this the process is actually the simplest possible example of these combinatorial Dyson-Schwinger equations of physics, and which in general are coming exactly from a similar kind of structure where you again have an infinite a variable that's written as a sum of variables in the various degrees of some suitable algebra that describes your combinatorial objects, and you write a fixed point equation which is something like that. You have some kind of polynomial functions of this x, which in our case is just this quadratic function here. And you have a grafting operation that takes these monomials and grafts them together to a single object. And so this is the first parallel of structure between this generation of syntactic objects and this type of generative process that one sees in theoretical physics.
Okay, you're saying fundamental case because it's binary. And also because it's just grafting, I mean, the grading that you've chosen, that's why it's fundamental. Yeah, so
I mean, this would be, in this case, in a physics setting, that this structure would be, the trees that give you the structure of nested subdivergences in Feynman graphs, and would again be this grafting operation of trees that form combined together subgraphs into larger Feynman graphs, and these Dyson-Schwinger equations provide you with the underlying combinatorial structure for when you want to recursively solve the equation of motions in the order of expansion in the perturbative expansion. Okay, so these are the syntactic objects so far. So this is the way we're defining them. So what about these workspaces? Okay, so let's come back to the way that they are described in the linguistic setting. You want to carry out this process of structure formations of syntactic objects in over a bunch of or initial choice of lexical items. And of course, you think of your building structure as this sort of bottom-up operation where you start to put together some things in various parts of the workspace, and then as you keep going, they will coalesce into larger structures. So you have these intermediate steps at which some parts of structures are built and some are not yet built. and some are transformed, and so on. So you have this kind of place where this computation takes place, which at each step is updated by some operation. So the natural way to define this thing is to say that a workspace is a forest of non-planar binary rooted trees. So this is the disjoint union of a bunch of these objects. And of course, this includes in particular the case where the trees are just trivial trees that consist of a single leaf with a decoration by a lexical item, syntactic feature. So if you want, you can start out by just a disjoint union of a bunch of lexical items, and then but at the intermediate steps of structure formation, you will have a disjoint union of binary rooted trees with leaves labeled by your lexical items and syntactic features. Okay, and so it means that you want to construct merge operations that act on this set of forests. So they will the merge operation takes as a forest as input and produces a new forest as output. And so the next thing that I need to define is what is meant by accessible terms. These are the substructures that we want to be able to use in order to modify sentences that are already built. So the way you define it is simply in the following way. If you have a syntactic object, which is one of these non-planar trees, you pick any internal vertex, which is not the root in the whole thing. You just pick any internal vertex, or possibly a leaf. If it's a leaf, it's just that by itself. If not, you just pick everything that's hanging below that vertex. Okay, so that's an accessible term. It's if you want, it's an internal vertex, or it's the tree that hangs. If you want to think of it as a syntactic object itself, is the tree that hangs below that vertex. And for the workspace, there are two slightly different conventions in the linguistic literature. So I was to decide which one to use. So one of them describes as accessible terms of the workspaces, the accessible terms of each of the trees in the workspace. Or the other convention is that when you talk about accessible terms of a workspace, the entire components are also accessible terms of the workspace. Okay. So because they are themselves substructures of the whole structure. Okay, so these are like the two accessible terms, and I'm gonna just try to distinguish with some different sign whether I include the entire structure also as an accessible term or not. And so what is the formation of the individual syntactic objects is well described by this magma that I mentioned before. So what is the kind of algebraic structure that's naturally underlying workspaces given what I don't want to do with them? So I claim that the right thing to look for is something that's like a Hopf algebra. So why is that the right thing? Well, because a Hopf algebra is designed to keep into account two kinds of operations, some kind of assembly operation and some kind of disassembly operation. And these two have to be compatible with each other. Of course, compatible with each other does not mean that your disassembling operation is an inverse or that they are inverse to each other. In fact, it is typically the case in Hopf algebras that one of the two operations is like more interesting than the other one. So in this case, it would be the case that the disassembling operation is more interesting than the assembling operation. The assembling operation is simpler, but there still has to be a compatibility between the two. I'll review the actual definition in a moment. Oops, I'll review it next time. So anyway, just to make some concluding point on this. So the assembling operation, well, you just assemble a workspace, right? You're saying, okay, I want to start some structure formation. I have a bunch of lexical items that are gonna, become part of my sentence. So the first operation is that something that takes these partially built structures and puts them together. And so, of course, the disjoint union of trees that assembles a forest as disjoint union is the natural composition operation that you want to have. And the decomposition operation, I just said that in order to manipulate structure, you need to access certain substructures. And so the disassembling operation is the thing that allows you to reach inside already built structure and take out some pieces. And so that is the part that give you the co-product of the Hopf algebra. And so I'm gonna stop here, and I'll start next time by going more into detail about how these operations have to fit together and what one can do with the specific case that we are dealing with.